Hey everyone, welcome to this explainer. Have you ever looked at a massive, complex AI model, or honestly, even just the tiny microcontroller running your smart thermostat, and wondered how exactly does a machine process all of this using literally nothing but numbers?
How does a computer actually understand artificial intelligence? It's such a fascinating question. Because, surprisingly, computers don't understand English or Spanish or any human language for that matter. They only understand distinct numeric bases. So to really speak their language, we have to talk about things like binary, decimal, octal, and hexadecimal.
Okay, let's dive into this. Here is our roadmap for today. First, the language of computers. Second, understanding bases and positions. Third, binary, the hardware layer. Fourth, octal and hexadecimal systems. And finally, embedded tech and real applications.
All right, starting off with Section 1, the language of computers.
Think about how we humans communicate quantity. Whether it's a Roman numeral X or the number 10, the actual underlying value is the exact same, right? Only the symbols change. And really, that's exactly what a number system is. It's just a way of representing numbers using a fixed set of symbols. Then you have the base, which is simply the number of unique digits available before you have to start repeating yourself. Think of it like the odometer in your car. In our everyday decimal system, once that odometer hits 9, it runs out of symbols and physically has to roll over to the next position. Now, if it were a binary odometer, it would roll over the moment it hit 1.
Let's move on to Section 2, understanding bases and positions.
Let's take a totally familiar decimal number like 5,728. In this system, every single digit has a specific positional value based on powers of 10. So that 8, it's just 8 times 10 to the power of 0. The 2 is 2 times 10 to the first power. The 7 is 7 times 10 squared, and the 5 represents 5 times 10 cubed. You add all of those up, and boom, you get 5,728. The crazy thing is, every single number system in computing, right down to the tiny microcontroller inside your microwave, works exactly like this. They just use different base multipliers.
And this brilliantly illustrates the difference. In Desmo, on the left, we comfortably count from 0 all the way up to 8. But look at binary over on the right. With only the symbols 0 and 1 available, it immediately runs out of symbols and rolls over to 10, which in binary actually just equals 2. By the time we reach the decimal number 8, binary has already rolled over so many times that it's written as 1000. It's kind of wild to look at.
So let's zoom in a bit. Section 3, binary, the hardware layer.
Electronic circuits are easiest to build using two states, voltage off, voltage on. This quote really hits the nail on the head. It all comes down to a fundamental truth of electronics. Inside modern CPUs and embedded microcontrollers, you literally have billions of microscopic transistor switches, and they can only be in one of two physical states, off or on, 0 or 1. It's those billions of tiny switches working together in perfect synchronization that creates every single piece of software, every high-definition video stream, and every complex AI model you interact with.
Let's see how this builds. Imagine an 8-bit register. This is the exact kind of hardware you'd find in a basic embedded system. Notice how every active bit, every 1, has a specific weight based entirely on its position: 64, 32, 8, 2, and 1. If we just add up the values of those active bits, we get our total decimal conversion. This is exactly how we translate the machine's strict, hardware-level binary logic directly back into our comfortable, human decimal world.
Zooming back out a bit. Section 4, octal and hexadecimal systems. Let's start with octal, or base 8. As you might guess, this uses the digits 0 through 7. Now, while it was incredibly significant in early computer architecture, it totally still survives today. If you've ever had to set file permissions in a Linux operating system, or maybe you've tinkered around with certain legacy embedded tech, you have directly used the octal number system.
Then we have hexadecimal, or base 16. This one is absolutely everywhere in computing. But here's the catch. Since we need 16 unique symbols before we roll over, and we humans only have 10 numbers from 0 to 9, embedded engineers had to get a bit creative. They actually borrowed letters from the alphabet. So in hex, A equals 10, B is 11, all the way up to F, which equals 15. Now, what's really interesting about this is how it solves a massive headache for programmers. Notice that long, unwieldy binary string at the top?
It's super difficult to read and honestly way too easy to mistype. But because one hexadecimal digit perfectly represents exactly 4 binary bits, that massive string funnels down into a much shorter, highly compact hexadecimal equivalent. It's a lifesaver. It literally saves programmers from having to type out endless screens of ones and zeros.
Let's connect this to the real world. Section 5, Embedded Tech and Real Applications.
So, you can see that each system has a very distinct practical purpose. Humans, and things like our daily banking, rely on decimal. The bare hardware itself, the CPU, RAM, logic gates, that strictly uses binary. Linux environments and legacy tech rely heavily on octal. And hexadecimal, that is the absolute go-to language for programmers when dealing with memory addresses, colors, and embedded systems. Understanding how all 4 of these interplay makes debugging electronics and programming significantly easier and a whole lot faster.
In fact, these systems are working behind the scenes constantly. When an embedded computer looks up a memory address, it's often reading a hex value like 0x7ff3a. Or, when you pick a really vibrant RGB color code for a web design like #FF5733, that's hexadecimal too. Even writing direct binary values in C++ for your DIY Arduino projects, or sending network packets across the internet, it all relies entirely on understanding these specific number systems.
So, the crucial point here is that all number systems use bases and fixed symbols. We inherently use base 10. The bare metal requires base 2, and software engineers elegantly bridge that gap using bases 8 and 16. This knowledge isn't just fun trivia, it is the absolute bedrock of all computer architecture and embedded systems.
Which brings us to our final thought for this explainer. You now know the language of machines. You know exactly why they use it and where it's applied in the technology all around us. The question is, are you ready to step beyond theory and actually speak it? Mastering how to convert and manipulate digital electronics step by step yourself is what really unlocks the true power of embedded systems. Keep exploring, keep learning, and I'll catch you in the next one.